Welcome back, everybody. This first example will be a two-tailed test for two population portions. This is how it reads. A study investigated the survival rates for in-hospital patients who suffered cardiac arrest. Among 58,593 patients who had cardiac arrest during the day, 11,604 survived and were discharged. Among 28,155 patients who suffered cardiac arrest at night, 4,139 survived and were discharged. We want to use a 1% significant level to test the claim that the survival rates are the same for day and night patients. Okay, step number one of the five-step procedure of the critical value method is to establish the hypotheses that are being tested. The null hypothesis says that the proportion of those who survive from cardiac arrest between day and night are equivalent to each other versus the alternative statement, which says they are not equivalent to each other. So basically, we're just trying to see if the proportion of patients who have cardiac arrest and survive are the same between the nighttime population and the daytime population. We're going to test these hypotheses at 1%. Step number 3 now is to compute the test statistic value. And this is our test statistic formula here. Before we can actually crank out our test statistic, we have to compute what is called p-bar, which is a pooled sample proportion. And p-bar for this example is going to be the sum of the patients that survived cardiac arrest for the day, 11,604, added to the number of patients who survived cardiac arrest at nighttime, 4,139, divided by the sum of the sample sizes, 58,593 plus 28,155. And when you crank this out on your calculator, make sure you enclose your numerator and your denominator inside parentheses to stay off a logical error. When you compute this ratio, you get 0.18. So that is called p-bar. We take p-bar now, this 0.18, and we bring it up into this formula here to compute our test statistic value. And so in the numerator, we're going to have our sample 1 proportion subtracting off the sample 2 proportion. Now, sample 1, I'm designating as being the sample that comes from the daytime survivors of cardiac arrest, and sample 2 is going to be the nighttime survivors of cardiac arrest. It really doesn't matter in this case which one you call sample 1 or 2, as your conclusion regarding the test will be the same since we have 2 rejection regions and perfect symmetry underneath the normal distribution. Of the 58,593 patients that suffered cardiac arrest during the day, 11,604 were successfully discharged and survived. So we take 11,604 divided by 58,593 minus the nighttime crowd, which is 4,139 survivors divided by 28,155 nighttime patients who suffered cardiac arrest. We're going to take that difference and we're going to divide it by the square root here, where we take p-bar, which was computed earlier, which is 0.18, times 1 minus 0.18, and we're going to divide that product by 58,593. That's for the daytime crowd. The nighttime crowd is 0.18 times 1 minus 0.18 rather, divided by 28,155. When you put this into your calculator, you should get 18.32. Now, this is a very complicated calculation, and if you do not input this correctly in your calculator, you're going to get what's called a logical error. And so the way to put this into your TI-84 calculator is to type it in this way. Let me zoom out a little bit here. So this, ladies and gentlemen, illustrates how to type that calculation into your calculator accurately. You have an open parenthesis, 11,604 divided by 58,593, subtract 4139 divided by 28,155, closed parenthesis, divided by, now the denominator. You have to get your square root function. Second button followed by the x squared button. Then you type in 0.18 times, open parenthesis, 1 subtract 0.18, closed parenthesis, divided by 58,593, plus 0.18 times, open parenthesis, 1 subtract 0.18, closed parenthesis, divided by 28,155, closed parenthesis, and finally enter. If you type it in exactly that way, you will get the correct test statistic value, which should be about 18.32. Now, step number 4 is establishing the rejection and the acceptance region, and this is a two-tailed test. And so therefore, we're going to have two rejection regions, one in the lower and upper tail of the standard normal probability distribution. The size of these rejection regions is going to be our level of significance, which is 1% divided by 2. So 0.005 will be the size of the lower tail, and 0.005 will be the size of the upper tail rejection regions. Notice the middle of the curve is designated as the acceptance region of the null hypothesis, or the do not reject region of the null hypothesis. All right, to find these critical z values, you're going to use on your calculator your inverse norm function. So you go get your inverse norm function, and you type in the area to the left of your critical z value that we want to find, which is 0.005. And the mean of the standard normal distribution is always 0, and the standard deviation of the standard normal probability distribution is always 1. When you type that in, you should get negative 2.58 as being your lower tail critical z value, and by symmetry, our upper tail critical z value will be positive 2.58. And now, ladies and gentlemen, we're ready to make a decision regarding our hypotheses here. Notice our test statistic, which was computed up here, was about 18.32, and 18.32 is greater than 2.58, and so it falls very safely into the upper tail rejection region of this normal distribution. And because of that, sample evidence is strong enough to suggest that we are able to reject the null hypothesis. We are able to reject the null hypothesis here, and therefore the claim is not being supported here, because the claim was that the proportion of survivors from cardiac arrest between day and nighttime is the same. But since we're going to reject our null hypothesis and go with our alternative hypothesis statement as being true, the claim is not being supported by sample evidence, because we're going to reject the null hypothesis statement. So essentially, sample evidence is showing that the proportion of survivors of cardiac arrest from those during the day versus the night are not equal to each other. And we only stand a 1% chance of committing a type 1 error and rejecting the null hypothesis, which may in fact be true. But since that's such a low level of risk, this is a very conclusive hypothesis test. So without a doubt, we are going to reject the null hypothesis, and therefore say, in plain English, it appears that the proportion of survivors of cardiac arrest between the daytime and the nighttime patients is not the same. That concludes this two-tailed hypothesis test involving two population proportions. Okay, this next example is going to be a lower tail or a left tail hypothesis test involving two population proportions. And this is how it reads. In a randomized controlled trial in Kenya, insecticide-treated bed nets were tested as a way to reduce malaria. Of course, malaria is a deadly disease transmitted by mosquitoes. Among 343 infants using bed nets, 15 developed malaria. Among 294 infants not using bed nets, 27 developed malaria. We want to use a 1% significant level to test the claim that the incidence of malaria is lower for infants using bed nets. Intuition would tell us that if bed nets or screens are used, then the infection rate from malaria carrying mosquitoes would probably be less. Well, we're going to formally test these hypotheses, and so therefore the claim turns out, in this case, to be the alternative hypothesis statement, which says the proportion of infant deaths attributed to malaria is less than if bed nets are used than if bed nets are not used. Okay. And of course, the null hypothesis statement would say that the proportion of deaths are the same between infants that were using bed nets versus not using bed nets in protection against the mosquito that carries the disease. We're going to test these hypotheses at 1%. Of course, this will be a lower tail test since we have the less than symbol in our alternative hypothesis statement. Our test statistic, again, is going to be computed using the aforementioned formula. Of course, we have to compute P bar first. And so of the 343 infants using bed nets, 15 developed malaria, plus only 27 developed malaria not using bed nets, divided by the sum of the number of infants that were randomly surveyed. 343 infants that used bed nets were surveyed, added to 294 infants that did not use bed nets. Again, enclose the numerator and denominator inside parentheses to stay off a logical error. You should get 0.066 as the p-bar value. Take 0.066 now, incorporate it into the test statistic formula up here, and notice all the other numbers drop in place. So my sample 1 proportion is coming from the infants that did use bed nets. My sample 2 proportion is coming from the infants that did not have bed nets. Okay. So anyways, you drop the numbers in place where they belong into the formula here, and then you get on your calculator and dial this calculation up, typing it in the same way that you typed in the previous example. You should get a test statistic which is negative 2.44. Step number 4 now is clearly establishing the rejection and acceptance region, and since this is a lower tail test, the rejection region will be found in the standard normal probability distribution, and the size of this rejection region will be 1%, the level of significance that we set back in step number 2. Getting on your calculator, using your inverse norm function to find this critical z-value, we type in the area to the left of our critical z-value, which is 0.01. The mean and standard deviation of the standard normal distribution, of course, is always 0 and 1 respectively. And when you type this in, ladies and gentlemen, you should get negative 2.33 as being your lower tail critical z-value. Now we're able to make a decision. Notice our test statistic is negative 2.44, and negative 2.44 is a little bit smaller, not much, but a little bit smaller than negative 2.33. And so our test statistic does fall slightly into the lower tail rejection region. And because of that, ladies and gentlemen, we are able at 1%, we are able to reject the null hypothesis, and then we're going to go with the alternative hypothesis as being a truthful statement. So it does look like, yes, sample evidence is supporting the claim that the proportion of infants who contract malaria is less for infants that use bed nets as opposed to those infants that do not use bed nets. So it does look like bed nets are making a difference in reducing the number of infected infants when bed nets are being used. So this concludes an example of a lower tail hypothesis test for 2 population proportions here. Okay, that concludes the lecture supplement that I attached in Module 13, in addition to your reading section 11.1 out of your textbook. I will also go over some other in-class examples of testing 2 population proportions, showing you the p-value method, the method that is used on the calculator instead of showing all 5 steps, which I did on these last 2 examples, using the critical value method. And so please do view those videos that will illustrate how to do these tests using your TI-84 calculator called the p-value method.